Good morning, everybody. My name is Boris Mejias. I'm a holistic system software engineer, more formally known as solution architect at EDB. I'm also an air guitar player. That's why I like a lot our slogan, Power to Postgres, and I'm going to use that power to wake you up because I know that it's very early in the morning for you. We're going to talk about in this session variation of PostgreSQL replication. The idea is to start going from the basic so that you can identify step by step how we get to a slightly more complex architectures. And because we are going to see each of the differences, you are going to be able to identify which one suits better your use case. And you get better informed and in the sense that you can take better decisions. Now, this is an open source conference. And because it's open source, I would like to talk about open source music. This year, the guitar player Kiko Loureiro made a very good release of an album called Open Source, which is actually inspired by the way that we work. And in terms of releasing software, making it available for people to study the software, to make changes, release new stuff, release variations of the creation. So makes like a new dimension of creativity. Now, the first track of the album is called Overflow, and it sounds like this. I love that, and I would understand if you didn't, especially if you're not used to the heaviness of the metal music. So it might feel like an overflow to you, and that would be kind of the reaction if you don't know all the possibilities that you can get with PostgreSQL replication. And I show you a diagram like this one, where you have like 6 or 7 variations of different stuff. But we're going to get to this one little by little, step by step, as I told you in the beginning. So let's start with the beginning, the basics. The roots of heavy metal are based on blues and rock music, and the roots of PostgreSQL replication are based on backup and recovery. So look at the letters there. Is it a coincidence? Yeah, probably yes. It's just a coincidence. So let's continue with backup and recovery then. So when you have an instance of PostgreSQL, you have all the memory, all the things that are happening. You have your base directory, which is all your data on disk. And instead of changing every time those files, what you're going to have is you're going to keep a track of all the changes, which is your wall files. So everything that something happened is go to the walls. And then from time to time, you write from the share buffers to the data directory, which is your checkpoint. But if you crash in between, what you have is the wall files are going to allow you to recover the entire history of changes into your base directory. So it goes more or less like this. You have somebody who is reading a clean buffer, all fine. As soon as it changes the buffer, we want to store that change on disk before we tell the user or the application that the transaction is being committed. So first goes to disk, to the wall files, and only then we say like is committed, so that we have this possibility of doing the recovery in case of a crash of the RAM. Now imagine that the entire thing is crashed. Then you take, this is the principle of backup. You take a copy that you had already from your data directory together with the walls that happened while you were doing this change, and then you can do the recovery into a different machines, and then you apply the walls, and then you replay the whole stuff, and you have a physical copy which is exactly the same as the original one. Now the people for Postgres long time ago, they have a very good idea of saying like, why don't we just put another instance live while the master is still running? We don't need to wait until disaster recovery. We just copy every wall files and we send it from one wall directory to the other one, and we continually replay it. And then somebody said like, well, that's nice, but let's stream it every change, not just per wall file. So you have this process which is called the wall sender, which is going to read the wall, and it's going to send every change before it's even committed to the wall receiver at the other side, which is the replica. And then the replica is going to have this wall receiver process, which is going to write down to the file again in the wall directory all the changes. So at this point, it's exactly the same as the master. So the only thing that you need to have then for having a hot standby node is to apply these changes into the shared buffer so that the nodes that are connected to that machine can also read, and this become a read replica. So this is how it is built. It's a constant backup and recovery. I mean, the backup is original, the first phase, and then the recovery happens all the time and all the time. And because of that, when you want to know whether a node is a master or a replica, this also matches the terms of music. You have a master copy of your recording, and from this master you can create copies that are exactly the same, these replicas. But in this case, we are recovering all the time, so the master is changing also as well. So it will be like a live streaming. Anyway, so you ask in the master, is this node in recovery? Is it like false? Oh, then it's a master because it's not recovering from anything. Whereas a replica, is it in recovery? Yes. Okay, fine. Why don't we have something like say like, is this master, is this replica? Well, because they're basically doing recovery. So this is what it defines. It's like in metal. If you're playing a blues scale, which is possible to do in metal, nobody says like you're playing a metal scale just because it's in a metal song. It is still a blues scale. It is from the basics, from the roots. And that's why here you're doing replication, but you know that the roots are in backup and recovery, and that's how you query. So let's continue. You saw the wall sender, which is sending data to the receiver, to the replica, and it wants to know whether the value is being received or not. So it needs an acknowledgement. So this is like when the musicians want to know whether they are being heard by the crowd and say like, "Can you hear me?" The crowd say, "Yeah." Exactly the same. So you have this table or view called PGStat replication. I'm not showing all the columns, only those that are relevant for this presentation. And it says that it's streaming. You can see the state is streaming, and the sent LSN is like, "Can you hear me?" It is the value of the change that is being the last one that is being sent to the receiver, and then you can see the things that are being acknowledged already by the replica. So the replica is going to tell, I got this and I send it to the kernel, which is the write LSN, and then the flush LSN is to guarantee that it's effectively physically on disk. Once it's on disk, you can replay it, so make it available to the users or sessions that are connected to the replica. That's the replay LSN. And this is just in terms of the values of the LSN. You can also have this in terms of seconds or milliseconds, with the three columns there, the reply, flush, and replay, flush, and write lag, the three that from bottom to top that you can see there. Now, note that this is asynchronous communication. And that means that the commit happens locally, and then it's going to be replay remotely. So it is asynchronous. It doesn't wait for the other one to be in sync to continue, which makes things much faster. And most of the time, this is just what you need. I mean, if you don't want to lose any data at all, then you need a solution which is called synchronous replication that we're going to see in a minute. So let's continue. Remember, it is based on backup and recovery, and it's constantly recovering, getting the changes from the wall sender, getting to the receiver, and then apply to the shell buffers. Those are the roots. Let's go back to the tree then. We have the heavy metal tree, which is having the roots in blues and rock, and we can have variations of heavy metal. Let's say the classic heavy metal like Iron Maiden. You can kind of add lyrics that are more like about fantasy, like motivating you for happiness and courage, and an upbeat, which is a little bit more like powerful. Then we call this power metal. Okay, so power to Postgres, power metal, upbeat, go there, happy and courage. And if you take power metal and you add a violin, what do you get? You get folk metal. The upbeat is not at that much, then you reduce a little bit the beat, but basically if you add a violin to power metal, you get folk metal. Now if you add many violins, then you get symphonic metal. Yeah, so these are variations from the main part, which is heavy metal. I'm not going to continue with the rest of the tree because we want to see physical replication. And what I want to explain you is that it's kind of the same thing here. You change a little bit of some settings, some properties, some architectural design, and from the route that you have backup and recovery, and you get to the physical streaming replication, you can get to cascading replication. You change some parameters, and then you get to synchronous replication, which guarantees you zero data loss in terms of replication, but it requires more resources from your system in terms of how many machines you need and all this stuff. We're going to see that. But another change, which is not that big, but it makes a significant difference in terms of building new things, it is logical decoding, which allows to have logical stream replication. And this is, for me, a game changer. And we are going to see how you can exploit it in this presentation. So let's continue. We have asynchronous replication. A master node sends its changes. It is being received by the replica. I'm going to use the arrow with a black head for the for the replica, and this data is available for the sessions that are connected to the replica. But it's not limited to one replica. You can have multiple replicas as long as the master can have enough processes for sending all the information to the replicas. And because of this, each replica can be a read node. And what we are going to do is you're going to split the operations read-write to the master node, and everything that is read-only, we can send them to the replicas. Now, there are some tools that allow you to do this transparently, but it requires more processing of the queries, and it can have some errors. So what we prefer is take two channels. Your application knows which operations are read-only. So if you're going to perform a read-only, you just send it through the channel that does only the read replicas, and then that's it. And if you're going to write something, you go through the master. So you have two channels at the level of the application. And you can also have a connection pool in between, like PG Bouncer, that allows you to do this slightly more transparent for the level of the application in terms of the names and what are the nodes being the master and being the replica. Okay, but that's a different story. So this is what we call horizontal read scalability, because you can add more replicas, and then you can add more nodes for reading. Yeah. Now robustness. Imagine that you have your master and your replica, and the idea is that if the master crashes, your replica is able to take over and be promoted and become the master as well. And then this is going to be the new node that you have. So this is the typical architecture when you have two nodes, master and replica, and they're both running usually in the same data center. If the data center crashes, what do you have? Well, you need to have another data center. So this is two locations, which is going to add a different scale factor for your robustness. Now you have more tolerant to failures. Now you can have an entire data center that crashes and you can continue working. That's very good. So what you can also have, and then here we go cascading replication, and it was a variation added at a certain moment that somebody receiving the stream can also produce the same stream to another node. And the idea here is that imagine that you have to pay for the transfer between two data centers. In this case, you pay only once, and then this other node is going to be able to stream things back to the other node. And then you have four nodes that are connected like this in two data center, and this is what we call cascading replication. It can have different architecture, stuff like that, but this is the basic idea. So now you know what it is and why is it useful. Okay, so you add more robustness. If you want to have automatic failover, I'm always very cautious about proposing automatic failover, because you need to have at least three data centers, three different locations. The most difficult thing here it is when a node cannot connect to another node. Is it because the network is broken, or is it because the other node is really unavailable and crash and dead? So because of that, you need to have another node which is called a witness. That's why I put an eye here, which is the eye of the beholder. It doesn't really have to be another Postgres node. It just need to be able to talk to everybody and then observe them. And then when something goes wrong, you can contact the witness, and then you can decide together with the witness, you're going to have one data center plus the witness, and then you're going to be the majority. And with the majority, you can carry on. Or if you cannot see the witness nor the other nodes, then you're isolated. You better decide, like, either you shut down to avoid having split brains, or you wait and stopping all the possible writes until everything comes back. So if you want to have another level of robustness and you want to have some automated decision between who is the new master and who is down or not, you really need to have a third data center. It's not, or at least a third node. It's not possible to have it only with two parts, two blocks. It's too risky. Yep. So something different that I'm not going to add a new set of slides. I just want to add it here because this one protects you from crashes from the machines or the network, routers, everything. You can also protect yourself against human error. Yeah. So you can have one of the nodes, for instance, the cascading node, which is delayed in terms of applying the changes into the share buffers. That means that if somebody by accident deletes a table or changes a value that shouldn't have changed on the master, this is going to be immediately replicated to all the nodes. This one is also going to receive the change, but it's just going to wait for a certain amount of time. It can be anything, 3 hours, 4 hours, it doesn't matter, until it applies the change. That means that you have time to post that node from replay anything, find the data that you need, and then reapply it back to the master. Instead of doing stop everything, point in time recovery, lose some data, or replace some stuff. This is actually kind of a good way of protecting yourself from human error if you have enough nodes. Okay, it is also kind of useful for when you have auditing nodes that perform a lot of data warehousing. When you don't want anything to change, you just want to run the queries as fast as possible. And then once you finish these operations, which are very long running, like half an hour or 1 hour, then you replay again and you catch up everything. Now, how does it work? It's really a variation. It's just a variation in terms of when you apply the changes. So you're going to receive all the walls, yeah, exactly like any other replica. That means that if your master node crashes, you already have all the changes that you need. You just apply them late. You just say, okay, this is I'm not yet in my time out of 3 hours. I'm not going to open this change. Yeah, so it's not also that the master needs to keep information for you for 3 extra hours. No, it just sends you everything, and it's up to you when you're going to open the envelopes, keeping the walls. So that's how it works. It's very simple, and it allows you to have some protection for human error. Now, data loss. What I was explaining is that if you have a master in your replica doing asynchronous replication, if the master crashes but first informed the application that it committed the transaction but didn't have time to send it to your replica, this is what we call data loss, because the application thinks that it is fine, but it's not. It's gone. So imagine that you have transaction for money and stuff like that, which is, you don't want to lose. Then you really need synchronous replication. So let's see how it works. You have, again, your continuous recovery of data. You want to know at the application level, when is it committed? So it can be committed locally, and then all the rest is done after. That's asynchronously. Or you can say, I want to synchronize my replica, and then we go back to this view, the PG stat replication. You can see the synchronous state is sync. That means that only when my replica tells me that it's ready, I assume that it's ready. This one needs also some extra information. For instance, you need to know the other application, so the other replica. So the replica is going to connect with an application name, in this case called metal, and then you're going to decide when it's going to be synchronous. It could be either when it's being received at the other side, when it's being flashed to disk, or when it's being available already at the other side. So you have 3 levels there. Now, what does it mean here? So you have this synchronous mode, which can be on, and this is going to be either local or remote, but it's always going to be on the wall files. When the walls have it on disk, this is on, synchronous commit on. Remote write means this intermediate step between the receiver and when it sends it back to the wall, down to the wall. And then the remote apply, as you can see on the graph, it is when it's available on the share buffers for the other nodes. Yep. That's the 3 levels. Now you have the variable set to local. That means that you have a set of nodes that can be your synchronous replica, but you're not going to use them because you just want to have everything local, and you're going to change that dynamically. Only some of the transactions are going to be remote. Okay, so synchronously remote. So let's get back to the table, the view. This is one of the things that you have to look for when you have a synchronous replica. And you have here also priority, which is the first one. Metal is the first node that you want to have. How do you configure this on your database? You have a set of names which are called the synchronous standby names, and you can say when the first one gets the data, I'm okay with the synchronicity, and I tell this is good. In this case, I have 3 replicas called metal, rock, and blues. If I want to have a larger amount of nodes, so if my master node and the metal node fails, I also want the rock node to have the data synchronously, and then you say like the first 2 of this list need to have the value. If some of them dies in between, you need to have some timeouts and all this stuff. Okay, but you can also say like any of these 2, any 2 of these 3, any either metal and rock or a metal and blues, if they say that they have it, then I'm fine, it's okay, and you can continue. So you have all these possibilities. Now remember, for the synchronous commit, you can decide when it's going to be considered synchronous, and you can also decide to be local for all of them, except for some of them that you want to do dynamically. So use this local thing here, there, boom, only when you want to add dynamic synchronous commit. So this is the next step. Synchronous when it's important. You have any one in this case, not any two, but any one of these three nodes, if it says that it got the transaction, I say that it's fine, it's synchronous. And but in general, I'm just going to be doing local. So at this moment, with these two configurations here, everything is asynchronous, but locally synchronously commit. When it's important, then I can change my commit status, and I say like, for this session only, not for the entire instance, only for this session, I want to set synchronous commit to remote apply. So my change have to be available already at the other side. I'm connected here to the database Vaken, yeah, which is homework. You have to search what is Vaken in the world of metal, and you have somebody ordering beers, and so item, quantity, beers, and it orders 18 beers. Not because he's going to drink a lot, but because you have some friends and all the stuff. And 18 is also a magic number. So this is 18 in binary. So if this is 01001, you get the number 18. This is 19. It's not good. 18. So this transaction, it is synchronous. It's not going to say committed until it's being available in at least any of the three nodes that I consider as my standby names. And then when I finish my transaction, which is very important, then I say, okay, reset the synchronous commit status so that everything is asynchronous, and we're fine. Right, so note that I changed the head now. It's a white head. This is a synchronous commit. But when you have only two nodes, this is bad. This is a fragile synchronous commit. Why? Because now instead of having one single point of failure, you have 2 points of failure. Because if the replica crashes and you want to have synchronous commit, the master cannot write anymore because it needs a replica. So to increase that, you need to have at least two nodes for doing synchronous replication. Otherwise, it's going to fail in a certain moment. Don't do it. You can also have it with two data centers. So you have one which is locally always synchronously commit very fast, and in case that this one fails, you have a safe point on the other node, which is fine. And then that one can be combined with asynchronous with cascading replication. So it's also possible. Now you can have here all the synchronous commit can happen in the same data center, but everything that goes to the other data center is asynchronous. This is still more robust in that sense. So the entire data center is gone. You might have some data loss, but not important ones because you can change those. And then you get the other data center available. Okay, so remember, you can do this dynamicity. So you have your node that can be all asynchronous, and from time to time you have these two that can be synchronous. Yeah, so you can play that with every transaction. Let's go back to our tree. I told you that we were going to talk about logical replication. I have enough minutes to tell you about the main change that happens here. So this is physical streaming replication, and the main things, which is a small thing but it makes a huge difference, it's a variation, is the logical decoding here. And this means that you are going to be able to have a change that can be interpreted logically by any type of Postgres that can decode this information. Then you have the logical downstreamer, not the whole receiver anymore, but the logical downstreamer. So it gets a change and it's going to apply it to the shared buffer so that it can be available for the users. And this is going to go then through the same process to get to the wall file. So it is like another writer on that system. And logical downstreamer, that sounds like a song from Ronnie James Dio, the Stargazer, the Holy Diver, the downstreamer. Yeah, so it's cool stuff. I like it a lot. So this changes a lot. And the thing is that you don't have to copy the entire instance. You can copy only one database, only a few tables. But because of this, you don't have, when you create a new user, you have to create it also some way at the other side. With PG Logical, you can also do some DDLs that can be replicated at the other side. So there's some support for doing DDLs and stuff like that. But it changes. It's mostly the data that is being sent to the other node. Yep. And it can be a master node here, and the other side you see that it is not really a replica. This is another master. So what you have here is a master multi-master, not in a bidirectional way, but in a way that you can write on both nodes. Yeah, so this is very important, very crucial. The main use case, it is simply for doing online upgrade, so you have nearly zero downtime. You can go from version 9.5. Note that I changed also the arrow now to version 12. And then if you're in the middle of the process, you can say like, okay, I'm moving this database from this instance, but I have another database on this instance, and I would like to move that one to version 13, for instance. Sorry. There you go. So you can upgrade your version and split your instance into two. That's also possible. You can also upgrade the entire cluster. So you have your cluster here running version 9.5. It is I chose the color gray because this is kind of almost out of support. So you better upgrade as soon as possible. Instead of upgrading one node and then create all the replicas, you can immediately create the entire cluster with version 13, and then you apply logical replication from the master of 9.5 to the master of version 13, so that you get everything is replicated immediately. Everything that arrives to the master in version 13 gets asynchronous replicated to the other nodes, and then your entire cluster is upgraded like that, and nearly zero downtime, because when you finish synchronizing, you go with the application from one version to the other, and you continue. So let's mix all this stuff like progressive metal does. It takes information from different influences from different styles, and then it makes its own adaptations with time and stuff like that. So we have one node which is running an old version. We want to upgrade it to version 12. From version 12, I can move some part of my data to version 13, and on version 13, I can move some part of my data back to version 12. This is not bidirectional replication. In the case that you need bidirectional replication, it's a different way of dealing with the data, and this one, it is only like saying this data is only going to be modified on version 12. It's just for you available for reading there. And if you write it, you can write it there, but it's not going to be sent back. You can have conflicts again, but at a different level, only in the target node. But this one can have a different set of schemas, a different set of tables that can be sent back to the other one, but then it is originally to be written here on the blue, dark blue node, and to be slightly modified on the light blue here, but not to send it back again. So this is not bidirectional replication. It's kind of mutually exclusive replication between two nodes. It's possible. Now this one can have cascading replication. As you know, we have like third variation, and this other node can have a combination of one synchronous node in the same data center plus multiple read nodes that can be in anywhere. So then another variation, there you go. And you can have one node that gathers all the information. This is usually typical thing for data warehousing, when you collect all the information coming from different nodes. Instead of having, it's not possible to do it with physical replication, but now with logical replication, it is possible. You don't need to have triggers or anything. You just set a publication of things that you want to send to that node, and this one becomes the subscriber, and then he collects all the nodes, all the information from all the other nodes. Now, of course, backup is always important, but instead of having a backup and then copying files all the time, you can also have streaming. So first you copy all the files that you need, and then you stream from the different nodes. The old node is only possible to do it from the master. New versions can also be replicated and streaming from the replicas. As you can see, the two nodes on the down part here. And of course, the data warehouse is only one node, so that one is all, of course, forced to sync from that one. So you can see another variation now apply back. So we started from backup and recovery, we went to replication, and then we send it back to backup and recovery so that we can have also some streaming there. All a nice combination. Now suddenly this diagram looks pretty obvious to you. It's like, okay, I understand everything. It's cool. So conclusion. Let's get back to this tree. You have the basic part, which is backup and recovery. You create physical replication by continuously recovering from the master, and then by adding slightly modifications, you can get synchronous replication, cascading replication, and a game changer, which is logical decoding, actually opens you for a lot more things that you can do, bidirectional replication, sharding, and stuff like that. It can be done automatically, it can be done a little bit local. It's up to you to decide, but that's part of entire this different topic. So, but logical replication is the key to open that. So feel free to explore any of this path and then try to see which one fits better your use case. And to conclude, really, I want to talk about again open source music, and I want to cite Kiko Loureiro, because what he said that inspires him the most is this way of sharing the code and then making it available for people to create their own stuff and improve it and do something different. he said in his work, I'm going to read this, it brings us a higher sense of community and enhances our creativity and possibilities. So why not take this concept of open source software to our art and to our music? So this is the last message that I want to give you. This is an open source conference. Share with the community your knowledge, your questions, and see you in the coffee break and the next conference when we see live each other. So thank you very much.